Welcome, folks. We are into our next unit of study. So this is going to be Unit 4/5. The high school, for some reason, likes to break this unit up into quadrilaterals. That'll be Unit 4, and then transformations, that's Unit 5. However, the two units, if we do it that way, are so short that the turnaround on them is just ridiculous. So we're going to scratch that. We're going to combine them. Not that necessarily they go together, but together they will make a long enough unit that it's going to feel like it's worth our while. So just heads up. So we're going to start in Unit 8 today, dealing with angles of polygons. So finally, something other than triangles, because we've been doing triangles forever, it seems like. So let's get started here. First thing we're going to look at is interior angle sums. In other words, how many degrees are on the interior? If we remember back to triangles, we keep coming back to those, we know and we're able to prove that there are 180 degrees on the interior of every triangle. So one way to do it, to figure out, well, what about quadrilaterals or pentagons or other figures, is to use a diagonal or multiple diagonals, as the case could be, from one point on the figure and see how many triangles can we generate. So for example, if I picked this point on the quadrilateral and tried to draw as many diagonals as I can, well, I can only draw one. All right, one diagonal out from that point. Cool. So any quadrilateral can be broken down into two triangles. So if I have 180 here and 180 here, well, that means there are 360 degrees on the inside of every quadrilateral. So whether it's a square, rectangle, whatever, you get the idea. For pentagons, so for example, let's say I started from that location. I would only be able to draw two distinct diagonals in from that location, breaking it up into three. All right, so 180 plus 180 plus 180 as it goes. So in this case, 540, and so on. Obviously, we can continue that pattern on out. And one thing that I notice is that while this has 4 sides, it only consists of 2 triangles. Or this has 5 sides for a pentagon, but only 3 triangles. So notice one pattern that seems to emerge is that the number of sides and number of triangles is off by 2 every time. I can take this number of sides, so we'll call it n, and then to get the number of triangles that we need, we just simply take n and subtract 2. Once we've got that, we can take that number, that n subtract 2, and simply multiply it by 180. And then that provides us our amount. So for example, octagons have 1, 2, 3, 4, 5, 6 different triangles on the inside. That almost looks like a seashell or something. But anyway, so we've got that many, 6 triangles, and if we multiply by 180, we get 1080 as the sum of the interior angles. So pretty cool pattern. So we can take that and generalize it and turn it into a theorem. So take a look. We have the triangle sum theorem. Well, now we've got the interior angle sum theorem. Oh goodness, we're really out of focus there. Let's see if it'll get back. Aha, there we go. So here's what the interior angle sum theorem says. It says, look, if we're dealing with a convex polygon, now remember, convex polygons look like this. In other words, all of the angles point outward. If we were looking at, say, a concave polygon, for example, one that I like to draw is the dart. It's a quadrilateral like that. This is concave. And remember, we know the difference between convex and concave is that if I were to extend these sides, the sides extended would go through the interior, where if I extend these sides, they would never go into the interior. So again, difference between convex, which is what we're talking about today, versus concave, which is what we're not talking about today. So if we have a convex polygon, and it has n number of sides, and S is the sum of the measures of those interior angles, then we can generalize this formula, that sum is equal to 180 multiplied by the number of sides, subtract 2. So for example, if I know I have 5 sides, then I would simply take that 5, subtract 2, get 3, multiply 1 by 180, and we get 540. So pretty useful little theorem. In terms of proving it, the proof is somewhat, well, we've given sort of a rough go of it there. Again, I would recommend taking your figures, breaking them up, and then showing each time that, hey, we can only get 2 fewer triangles, or excuse me, yes, 2 fewer triangles for each side. So for example, if I have 5 sides, 2 fewer is 3. Or if I had 10 sides, well, 2 fewer is, that's not a good 2, 2 fewer would then be 8, and so on. So we could use that as a way of proving how this works. So there are multiple proofs. So interior angle sum theorem, that's how that works. Let's talk about the outside as well, because while interior angle sums are unique for every different polygon group, exterior we'll find aren't so much. So take a look. If I drew the sides and extended them on a polygon, we'll only extend them off in one direction and do the same way all the way around. So you kind of get this pinwheel or water wheel effect. If I were to add all 5 of these exterior angles up, or if I had a triangle, let's draw a triangle since we always seem to keep coming back to those, and extend each of those sides, again we get the kind of pinwheel or water wheel effect. If we add up those exterior angles, whether it be on a triangle, pentagon, dodecagon, whatever, it doesn't matter. If the polygon is convex, then the sum of the measures of the exterior angles, one at each vertex, is 360 degrees. So the question here is, how in the world does that work? All right. Well, instead of looking at a pentagon, which is sort of out there, let's try just a triangle. Again, triangles are nice. They simplify things. So let's redraw it down here just so we have a little more space. Cool. And then let me grab a different color. We'll draw these extensions in red. There we go. So here's an angle here, another angle here, and then our final angle here. All right, so cool. And let's start numbering them off. So I've got angle 1. Well, actually, we'll make that 2, 3, and then we'll make that one 1. So cool. If we were to take angle 1, plus we'll call this angle 4. So the measure of angle 1 plus the measure of angle 4 is 180, right? The measure of angle 2 plus we'll call this 5. The measure of angle 5, angle 5, there we go, also 180. And then we'll call this angle 6. And then the measure of angle 3 added on to the measure of angle 6 is also, cool, 180. Excellent. Now, if I were to take all of these and add them together, so for example, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4, good Lord, plus the measure of angle 5, we're getting there, plus the measure of angle 6, sweet cheese and crackers. There it all is. So again, now all I did was redo the order, right? 1 and 4 were together up here, but I put 1, 2, and 3 together, just again so that you can see that, with 4, 5, and 6 together there on the other side. Again, the only reason I did that is just to make it easy to look at here. If we take our 3 180s, that's, what is that, 530? No, 540. 540. There we go. Watch what happens. Based on the triangle sum theorem, right? We can take those interior angles and add them up. I know this all together is 180. All right, so I'm just going to substitute all of this for a 180. And we know that because those interior angle measures, we know, already add up to that. So plus, oh, here we go again. The measure of angle 3 plus the measure of angle 4 plus the measure of angle 5. Good Lord, plus, oh, nope, not 3. Good Lord, I didn't want 3. I need 4, 5, and 6. Oh, it helps if you read what you write, Lamar. Come on. And then, of course, the 540. Excellent. So now that we've got that, we can take the 180 away. So if I take 180 away from 540, we get the measure of angle 4 plus the measure of angle 5 plus the measure of angle 6. Notice those are all of our exterior angles, and we get 360 degrees. And here's the beauty of it, folks. This basic proof that I just did will work for any figure. So we could duplicate the same thing here with our pentagon. Angle 1 plus angle 6, angle 2 plus angle 7, angle 3 plus angle 8, angle 4 plus angle 9, angle 5 plus angle 10. All those interior angles, in the case of a pentagon, would add up to 540, and then what would remain on the outside is just 360. And it works that way every time. I just did it with the triangle because notice it's a lot of algebra. That would have taken a lot longer to write out. This, a little bit shorter. But again, when we're talking about interior angles, they are unique for each polygon group. So pentagons are different than hexagons that are different than quadrilaterals. Whereas if we're talking about the exterior angles added together, that sum, it's universal. It's always 360 regardless of the concave polygon we're dealing with. All right, so just heads up. So let's look at some examples of the work we'll do today. Today's work is pretty basic, straightforward, not a big deal. It should be something that you can do with maybe a little bit of calculator help, nothing more than that. So we're going to find the sum of the measures of the interior angles for each convex polygon based on the number of sides. And once you get past 10, We typically don't name them. They do have names. A 32-gon does have a name, but it's a horrible, horrible name, and we're not going to get into the Greek. So we'll just call them 32-gons or 18-gons and so on. So remember our formula. It is 180, that's the amount inside each triangle, multiplied by the number of sides, subtract 2. So in this case, I would take 180, multiplied by n, subtract 2. So in this case, 32 subtract 2 is 30, and then it's just a straight multiplication game. So we can multiply that out and get, what's that, 540 and an extra 0. Cool. That's a lot of degrees. And remember, folks, the more sides we add, especially if it's a regular polygon, the more sides we add, the rounder and rounder the figure becomes, which is pretty crazy but true. So if we actually drew out a 32-gon, it would look almost circular. All right, an 18-gon. So the same story. We're going to take 180 and multiply that by 16. Again, we'll take n and subtract 2. So 18 subtract 2 is 16. So 180, multiply that by 16, 2,880 degrees. Cool. And then a 19-gon, well, we would do basically the exact same thing. The only difference is instead of 16, it would be 17. So 3,060 would be your work there. Pretty simple and straightforward. Let's try the next one. It says the measure of an interior angle, so just one. One interior angle of a regular polygon is given. Find the number of sides in each polygon. Cool. So there's a couple ways that you can work these kinds of problems out. Here's the way I think that is the easiest. I'm just going to draw random polygon sides here, right? We don't know what kind of polygon we're dealing with, doesn't matter. 140. So I'm going to extend this side. We know this angle here is 140. Well, that means its exterior angle, right, on the outside would be 140 taken away from 180. So its exterior angle is only 40 degrees. Well, remember, all exterior angles added together, regardless of the polygon, is 360. So what I can do is take that 360, divide it by the 40 I just found, and that will give me an idea of how many sides that we've got. Because notice each exterior angle, one of those matches up with one of the sides. So I can take that 360, divide it by the 40, and in this case we get 9, the number of sides that this particular polygon has. Right? And we can do that same thing throughout. So here, for example, if we had 170 instead of 140, that means there would only be 10 on the outside. So 360 divided by 10 would give me 36. And let's go ahead and write sides on here. That way we know it's not angles. Sides. There we go. And then if we did 160, again, we'd have 360 over 20. Again, that exterior angle, instead of being 40 this time, it would be only 20. We could divide that out, and we would get, what is that, 18? Yeah, 18. Cool. Simple enough. All right, let's try a couple more quick examples here, and then we'll let you go. Take a look. So we've got to find the measure of each interior angle using our given information. So here we go. Let's count up the number of sides we've got first. So I've got 1, 2, 3, 4, I've got 5. So that means I know 540 is where we're going to end up. Again, I could take the number of sides, in this case 5, subtract 2 is 3. So 180 multiplied by 3 would give me the amount that we're looking for, in this case, the 540. So I know all of this added together should get me 540. So let's start adding. I'm going to start with all of the x's first, since they're like terms. So I've got 1x here, 2, 3, 4, 5. So I know I've got 5x. Let's count up all the constants. So I've got 10, 20, so that makes 30. 35, subtract 5 is just 30. Cool. So if I add all this up, or excuse me, not add all this up, if I solve this, I can get x and then take it, plug it back in, either add or subtract, and get what we need. Cool. So let's go ahead and do that real quick. I'm going to subtract 30 on both sides. So that's 5x equals 50, well, no, 510. Make sure I put my 0 in there. And then we can divide that out by 5. So 5 goes into 5 once, 5 goes into 10 twice. Cool. So x is 102 degrees. So if we're looking at each angle here, we'll say 102 for E. If I take that 102 and add, what is that, 20, so that's 122 for that one. If we add 5, that's 107 for that one. If we take 5 away, that would be 90, what would that be, 97? Yeah, 97. And then if we add 10, that would be 1 12. Now, one thing I do recommend, in case you may have made a mistake, is just double check that real quick and add them all up. So if I take 102, 122, if I can get my calculator to work, 102 plus 122 plus 107 plus 97 plus 112. Yep, 540. I didn't do anything silly with my math. So good. All right, well, let's look at this last one. Isosceles trapezoid TWYZ with Z and Y being the same, with Z being 30x. So if this is 30x, that means this is also 30x. And then it looks like our other two angles, of course, would be equal, and they are 20x each. There we go. So remember, we've got a quadrilateral here, so that's 360 degrees that we have to work with. So if I add these together, that would be 50 and 50, so that's simply 100x equals 360 degrees. Divide both sides by 100. We get x is equivalent to 3.6. So then it's just a matter of taking that x and multiplying it through. So I can take 20, multiply by 3.6, and we get 72 here, 72 there, and then from there we can simply multiply that again, and we get, what's that, 108. Of course, with this being a trapezoid, we know this side here and this side here, the bases are parallel, so if this is 72, this has to be 108 because they are consecutive interior angle pairs. So that's another way we can get those amounts as well. Cool. So today, this is what we're working with, our angles. Again, just a quick reminder, if we're talking about interior angle sums, then it's going to differ from figure to figure. So we'll need to use our formula to make sure we get that correct. If we're talking about exterior angles, remember, it doesn't matter what kind of polygon you're dealing with. They all will add up to 360 each and every time. All right, if you have any questions or concerns, let me know. Otherwise, have a good day.